Hi everyone. Let's continue. Let's look at this example 12. Consider g of x equals 1/2 sine pi x over 2. Part A. Show that there exists a unique fixed point in 0, 1 using fixed point convergence theorem. B. For xn plus 1 equals g of xn. Compute the error bound for x4 starting with x0 equal to 0. Determine the minimum number of iterations needed to approximate the fixed point to 10 to the negative 6 using x0 equals 0. Okay, so here, part A, we want to show there exists a unique fixed point. So we showed this before by using the intermediate value theorem and the mean value theorem. Do you remember? So we can also show this use the fixed point convergence theorem that we learned in our last video. Okay, so what is that? Let me review with you what is a fixed point convergence theorem. So let's go back. Okay, so we have three hypotheses. First, f of x maps AB into AB. Second, g prime of x is continuous on AB. 3, there is a number n such that the slope, okay, the n is less than 1 and such that the slope, which is the absolute value of the derivative, is less than or equal to n for all x in this interval. Then the conclusion is we can say g has a fixed point inside this interval. And furthermore, we have the error bounds ek less than or equal to n times ek minus 1. And the ek is less than or equal to n to the k times e0. Yeah, the error bound of e0. Alright, so let's use the fixed points convergence theorem. So what do we need to check? Well, we want to check g maps from AB. So the interval is 0, 1, right? And so if x is in 0, 1, then pi over 2x is in 0 to pi over 2, right? And then what does sine x look like? You know, this is sine x. From 0 is 0, from pi over 2 it equals 1, right? So it is an increasing function when the angle is from 0 to pi over 2. So far, so good, everybody? So that's why we know that sine pi x over 2 is between 0 and 1. So g of x, which is 1/2 sine pi x over 2, is then between 0 and 1/2. So far, so good, everybody? So g, that's why we have g maps 0, 1 onto into 0, 1. Oh yeah, into 0, 1. So far, so good, everybody? So this is the first condition we need to check. Second condition, g prime. Let's see, what is g prime? G prime is 1/2 derivative of sine is cosine pi x over 2 times chain rule. Derivative of x is 1, so we have pi over 2, which is pi over 4 times cosine pi x over 2. So far, so good, everybody? Okay, and you can see this guy is continuous, right? This is the second condition of the fixed point convergence theorem. And the third one, we want to show that the absolute value of g prime of x, well, this is pi over 4 absolute values of pi over 2x. Well, we want to show this guy is bounded by a number. What is that number? You know cosine is the absolute value of cosine is less than or equal to 1. Well, then this guy is less than or equal to pi over 4 times 1, which is pi over 4. This is our n. So far, so good, everybody. So now we have verified the 3 hypotheses. Then we can say by fixed point convergence theorem, the G has a unique fixed point in the interval 0, 1. So far, so good, everybody. Okay, and then for the iterative scheme xn plus 1 equals g of xn, compute the error bound for x4. So starting with x0 is 0. Okay, let's look at the interval. The interval is 0 to 1, right? And x0 is here. Let's say x asterisk is the true value. Then e0 is the difference between the true value and the x0. We can see this is at most 1, right, everybody? Because that point lies within this interval. So we have e0 is at most 1. And then we're looking for e4, right? So e4 is less than or equal to the formula n to the 4 times absolute value of e0. N is pi over 4, right? Pi over 4 to the 4 in e0 is less than or equal to 1. So we get pi over 4 to the 4 is our answer. And what is that number? Calculator here. So we have pi over 4 to the 4. 0.3805. Okay, 0.3805. So far, so good, everybody. Okay, so this is the error bound for x4, starting with x0 is 0. Okay, so part C is the other direction, right? We're given that the error is within 10 to the minus 6, and we want to find the minimum number of iterations. So we want to find k such that ek 0. So this is pi over 4 to the power of k, and e0 is 1. So we want this guy to be less than or equal to 10 to the minus 6. So far, so good, everybody. Okay, and so keep that in mind. We can apply ln on both sides. And then we can move the k down in front. Okay, is that, well, notice that pi over 4 is less than 1. So ln of pi over 4 is actually negative. When you multiply by, when you divide by a negative number, that will flip the inequality, right? So we have ln of 10 to the minus 6 over ln of pi over 4. So far, so good, everybody. And what is that answer? Wow, that's approximately by calculator. Where are you? We have ln of 10 to the negative 6 divided by ln pi over 4. Okay, and that's it. We click enter. Ooh, 57.19. Okay, so what is the minimum number for k? Shall we pick 57? No, we need to pick an integer that is greater or equal to 57.19. So we have to pick 58. So far, so good. So we need 58 iterations so that our errors will be within 10 to the minus 6. Okay, so this is about the fixed points convergence theorem. All right. Okay, now let's continue. So, notice that the fixed point convergence theorem give us a linear convergence, but sometimes depends on the function, we might get higher convergence. Okay, so first let's recall the Taylor polynomial. So we have g of x equals g of a plus g prime of a x minus a, and then let's say this is the nth order Taylor polynomial, right? And this guy is the remainder term. Let me put it down here. So this is the nth order Taylor polynomial. And this is the remainder term. Okay, the remainder term is really like the next expressions in the list, but instead of a, we put eta. Eta is some number between x and a. So far, so good, everybody? Then let's move g of a on to the left hand side. Then we have g of x minus g of a equals f prime of a x minus a plus the rest of the terms, right? Now suppose a is a fixed point. Okay, if a is a fixed point, g of a equals a. And also because by our iterative scheme, x sub n plus 1 equals g of xn. So now plug in x equals xn, and let's plug in g of xn to be xn plus 1. Then we have xn plus 1 minus a, okay, because a is a fixed point, that equals g prime of a xn minus a plus the second derivative over 2 factorial xn minus a squared, and the rest of the terms. Okay, so what does that mean? So this formula actually gives us more information. Okay, think about it. A is like the true value, the fixed point, the true value, right? This guy is like the error term at n plus 1, right? Okay, so let me put down here. If g prime of a is not 0, then we can say en plus 1 is approximately by g prime of a. This is en, right? So that's why it means the p equals 1. Now that rate of convergence is g prime of a, right? And then if g prime of a equals 0, why don't I press the remainder term? Because this guy is much bigger than the rest. Because when xn is getting close to a, well, this guy is a very small number. Think about it, if this is 0.1, then 0.1 squared, it would be 0.01. So the rest of the terms is very, very small compared to this first term xn minus a. Okay, so that's why it is enough to just consider the first non-zero term in this list. So if g prime of a equals 0 and g prime prime of a is not 0, that means the first term is gone. Okay, then we get en plus 1 equals g prime prime a over 2 factorial. This is this is en squared. So now you can see the p is 2, and then here the lambda is second factorial over the second derivative of g evaluate a over 2 factorial. Okay, so now you can see the order of convergence is 2. We can also keep going. If we keep going, then you will see if g prime is 0 and the g prime prime is also 0. Let's say if g triple prime is not 0, then we will get en plus 1 equals triple prime over 3 factorial, and this is en cubed. So in this case, p equals 3, lambda equals triple prime of g evaluate a over 3 factorial. See? So this is actually tell us more information. Okay, compare with the fixed point theorem. Okay, let's continue. Let's look at this example. So consider the iterative scheme. So this is the iterative scheme. Okay, will this scheme converge to the fixed point x equals 1? If yes, find the rates of convergence and the order of convergence. So the iterative scheme is usually x equals g of x, right? And then x is the fixed point. So what is g of x in this case? Well, g of x is 1 over 9 x cubed minus 1 over 4 x squared plus 41 over 36, right? Is 1 a fixed point? Let's check. Is x equals 1 a fixed point? Let's plug in. So it's 1 equals 1 over 9. 1 cube is 1 minus 1 over 4. 1 square is 1 plus 41 over 36. Well, let's calculate the right hand side. 1 over 9 minus 1 over 4. Oops. You see what happened here? Oh, I should move this guy here. Okay. And plus 41 over 36. See? The answer is 1. Right? And we don't need calculator. We can do it by hand. 9 times 4 is 36, right? And then minus 4. So this is 9. Okay. Yes. How to get common denominator 36? We multiply by 9. And then plus 41. 4 minus 9 is -5. 41 minus 5 is 36. So yeah. So 1 is a fixed point. So far so good, everybody? Okay, and we also find g of x. Now let's keep this Taylor this formula in mind, okay? This Taylor series formula in mind. And let's see, what's g prime of x? Well, we get 3. Oh, so that's 1 over 3 x squared. When we multiply by 2, this is 1/2 x. And that constant, a derivative constant, is 1. Okay, so what's g prime of 1? We plug in 1, we get 1/3 minus 1/2. Oh, so the answer is minus 1 over 6. So far, so good, everybody. Okay, so because this guy is not 0, okay, then when n goes to infinity, we will get xm plus 1 minus a is approximately equals to g prime of a xm minus a, right? So the limit n goes to infinity, of absolute value of m plus 1 minus a over xm minus a to the 1 equals absolute value of g prime of a, right? Because the first term, the coefficient is g prime of a. So that is the rate of convergence. Okay, so far so good, everybody? Oh, sorry, the rate of convergence, I should put absolute value around it. Okay, so I should put absolute value around it. Because usually we put absolute value around the en plus 1 and en. Okay, and in this case, that number is 1 over 6, right? So order of convergence is 1 and rate of convergence is 1 over 6. So we get linear convergence in this case. So far so good, everybody? All right. And this picture is f of x equals g of x minus 1. And you can see it has a 0 at 1. So 1 is a fixed point of g, and 1 is a 0 of f. So far so good, everybody? So 1 is the 0 of f, 1 is the fixed point of g. So 0 and fixed point, they're different things. 0 means f of that number equals 0. Fixed point means g of that number equals to that number. All right, let's continue. So part B. How about the following scheme? Okay, so first we want to check what's the right hand side. The left hand side is like x, right? The right hand side, well, g of x is 1 over 9 x cubed minus 1 over 4 x squared plus 1 over 6 x plus 35 over 36. Let's check whether 1 is a fixed point. So it's 1 equals 1 over 9 minus 1 over 4 plus 1 over 6 plus 35 over 36. Let's see, the common denominator is 36. 1 over 9 is the same as 4 over 36. 1 over 4 is the same as 9 over 36. 1 over 6 is the same as 6 over 36 plus 35. Okay, 4 minus 9 is minus 5 plus 6 is 1. 1 plus 35 is 36. Yeah, we actually get 1. So 1 is a fixed point. Now let's keep taking the derivative. Well, the derivative 3 times 1 over 9 is 1 over 3 x squared. 2 times 1/4 is 1 over 2x. The derivative 1 over 6x is 1 over 6. And let's plug in 1. 1 over 3 minus 1 over 2 plus 1 over 6. Ooh, that is 0. Right, everybody? And then the second derivative, we get 2 over 3x minus 1 over 2. G prime of 1. When we plug in it, we get 2/3 minus 1/2. Oh, this is the same as 4 over 6 minus 3 over 6. So 1 over 6. Because it's not 0. So we know the order is 2, right? And what does that mean? It means this guy is gone. Then we have this guy is approximately by second derivative evaluate at a over 2 factorial times the error en to the square, right? Okay, let's copy it down here. So as n goes to infinity, it looks like xn plus 1 minus a is approximately by second derivative over 2 factorial xn minus a squared, right? Because g prime of a is 0 in this case. So we have limits and goes to infinity, xn plus 1 minus a over xn minus a squared equals second derivative over 2 factorial. Well, that's 1 over 6 over 2 is 1 over 12. Okay, so we say the order of convergence equals 2 and the rate of convergence equals 1 over 12. A typical mistake is students will forget to divide the 2 factorial. This is a typical mistake. Okay, in general, the first non-zero derivative, you're gonna have, let's say if the k derivative, then you say the k derivative of evaluate at the fixed point over k factorial. This is the rate of convergence. So far, so good, everybody? Okay. I want to do some more with you. We know 1 is a fixed point, right? Why don't we use those iterative scheme to calculate? Okay, so let's check. Let's suppose x0 is 0. Okay, so let's see here. And let's see, B is right here. So let me copy down the scheme. So let me see. My first scheme is right here. Let me see here. Oh, okay. Okay. Let me print screen. Oops. Okay. Here. Okay, and where is it? Let's see. Let me move it here. Where are you? Okay. Okay. All right, so let me move it here, and then we can use our calculator to calculate. Okay, and we can compare the speed. Let me also do the same thing for xn plus 1. So here we go. Let's calculate. Okay. Let me use a table to denote. Okay. So this is x1, x2, x3, 4, 5, 6, 7. Okay. Now let's see. First step, 0. Enter. Second step, 1 over 9 times, oh, you see? Be careful. Move up, back. X cube, answer cube, minus 1 over 4, answer square, plus 41 over 36. Enter. Okay, so 1.3, 1, 2, 3, 4, 5, 6, 9. Okay, so 1.13. Okay, we get this number. Right, everybody? So let's continue. So we can just go up and enter again. 0.9787570.492. 9787570.492. Okay, let's continue. 1.003577032. 1.003577032. Easy? It's converging. We know the true answer is 1, right? And it's converging. And 0.99940489994. Okay? 0.99940489994. right? And continue. 1.000099213. Okay, continue. 0.999983463. 0.999983463, right? And then, okay, let's do this last one. 1.000002756. 1.000002756. See, it converges, and we get linear convergence. Let's look at the other one, right? Oh, x0 is also 0. And let's see. How do we calculate? We also need to input 0. And then we have our formula. Actually, our formula is very similar to what we had before, but we have inserts. Here is plus 1/6 times answer. So far so good, everybody? And we click enter. Well, the first number is actually the same as before, because when you plug in x is 0, what's left? Just the constant term is left, right? Okay. But as we continue and enter 1 point, let's see here. So 1.1. Oh, I just realized I made a mistake. The constant term need to change as well. So we copy that formula, but here this guy also changed as well. Changed to 35. Okay, so the first number is 0.97 and a bunch of 2's. So 0.97 and then a bunch of 2's. Okay, and let's see here. Copy it. Enter. 1.000061919. 1.000061919. And then, oh, you see at the third steps, we get to 1. And 1 is actually like 1 point, a lot of 0 outside, and then the calculator will show up just 1. So far, so good, everybody. So we can see, and because part B, the order of convergence is 2, so the order is the one matter. Okay, so we can see this guy converge faster. Okay, so if 2 iterative scheme, they have different order, then which order is bigger, that one will converge faster. If 2 iterative scheme, they have the same order, and then we look at the rates of convergence. Whoever has the smaller rates of convergence, then it will converge faster. So far, so good, everybody? Okay, let's continue to do more examples. So this is actually the last example in this chapter. Yeah, almost there. This session is quite long. I break it into, split it into 4 videos. Okay, so show the algebraic steps need to write the equation x cubed minus 3x minus 20 equals 0 in each of the following forms. Okay, so we want to show, so we want to solve this equation. Okay, so we want to show that we can rewrite these equations in terms of the following forms. So each form can give us an iterative scheme. So let's call this 1, 2, and 3, right? Let's look at 1. And you see how to show it? Well, you just do the reverse order. So starting with equation 1, let's multiply by 3 on both sides. Well, then we can move the 3x on to the right. We get x cubed minus 3x minus 20. Then we get our equation, right? And the second one, we multiply by x squared minus 3 on both sides. Then we have x cubed minus 3x equals 20. Move it to the left. We get our original equation, right? Last one, we can cube both sides. And then we have 3x plus 20. Okay, then we can move all the terms to the left-hand side. And we get it. So far, so good, everybody? Okay, so we can see. So just go backwards. Then we can get to this iterative scheme. Okay, now use xn plus 1 equals g at xn with x0 equals 3.5. Compute x7. Does it appear that each sequence is converging? If so, how quickly? Okay, so let's look at the first one. The first one, we have xn plus 1 equals xn cubed minus 20 over xn. Over 3. Right? This is the iterative scheme. We simply just replace the left-hand side x by x sub n plus 1. Replace the right-hand side, replace the x by xn. Okay? And now let's see. x0 equals 3.5. And let's see. We do x1, x2, x3, x4, x5, x6. Well, let's see what happened. Okay. Calculator, where are you? Here. Okay, so 3.5, enter. And then we do answer. Oh, parentheses first. Parentheses, answer minus 20 close parentheses divided by 3. Oh, I forgot to have answer cube. So, cube. So far, so good, everybody. Enter 7.625. So this is 7.625. So far, so good, everybody. All right. So now we just continue and enter, right? So copy this guy, enter here. Wow, 141.1074219. So we get 141.1074219. Wow, we can say it diverges, right? It does not converge. It's getting bigger. Oops. 936,537.6151. 936,537. Oh, sorry. When I copy it, okay. So 37.61. What is that? The next number? 51. You see, it's getting bigger. Let's do 2.7381 times 10 to the 17. Wow, so big. You see, it diverges. And a lot of iterative scheme will diverge. Okay, not many of them will converge. Wow, 6.8429. Okay, so 6.8429 times 10 to the 51? We know it diverged for sure. Ooh, 1.068, 10 to the 155. So it diverges. So far, so good, everybody? Yeah, so it's not converging, it diverges. Okay, let's look at the second formula. Second formula, iterative scheme is xn plus 1, 20 over xn squared minus 3. Okay, x0 is 3.5. And we do the same thing. If you don't mind, instead of x1, x2, x3, I just put 1, 2, 3, 4. Like the steps. Is that okay? 1, 2, 3, 4, 5, 6, 7. Is that okay? All right. Then let's see. We have, where shall we do it better? Let me see. Yeah, okay. Here. Okay, so we have 3.5. And then, oh, can we make it smaller? Okay. And then we have 20 over parentheses answer square minus 3. Okay, enter. 2.162162162. 2.162162162. So far, so good, everybody. And we copy it and enter. 11.94068.905. 11.94068. What do I get? Oh, 8905. Okay, again. Oop, wait. Okay, so we continue. 0.143286.9. Okay, 0.14328, and then 69473. 69473. Okay. They're not big numbers, but I don't think it's converging. Minus 6.712605. Okay. Negative 6.7126. And then what? 05837. 05837. Okay, let's do more. 0.475521. 0.475521. And then 6083. They're not big numbers, but they're also not converging. Right? We can't find a pattern. It's oscillating between plus or minus and numbers. We don't have a pattern. 7.21011. And then 9316. 9316. Let's stop here. Okay, so we can see it also diverges. Let's look at the third one. The third one, we have xn plus 1 equals cube roots of 3xn plus 20. Oops. Okay. So far, so good, everybody? Alright, let's draw the table again. So let's draw a table again. x0 is 3.5. And let those be the xi's. Okay. So here, 3.5. So let's clear. 3.5. And then we do 3 times answer plus 20. Close to the 1/3. So far so good. You can also do like the cube roots button here. Okay, so enter 3.124399885. 3.124399885. Let's see. Copy and paste, and you will go up and enter, or just click enter. 3.0854396. 3.0854396. And then 3.08134194. 3.08134194. Ooh, you see this? I think this will converge. It better be, right? We already have 2 scheme diverge. There must be a one it worked, right? This one worked. 3.080910293. So 3.080910293. And 3.0808648616. 3.0808648616. And it's converging, but it's converging slowly, right? So 3.080860025. 3.080860025. Let's do more. See whether it's stabilized at the end. 3.0808592. And continue. Oops. 3.080859467. Mm-hmm. 3.080859461. Oops. 59461. Almost there. Let's try one more. Oh, we don't have 46. See? Oh, good. It's stabilized. And then at the 11 one, we get the same. So why it shifts me again? So we get this guy converges. Finally. Okay. So far so good, everybody. I also want to chat with you what happened if we calculate the G prime and G prime prime, because those is gonna be like our rates of convergence and order of convergence, right? So let's see here. Let's use green. Okay, so the first one, G of x is x cubed minus 20/3. Well, that's the same as saying this is x cubed over 3 minus 20/3, right? And let's see here, G prime of x is 3 times 3 over 3 cancel, so we have x squared, right? And you see our number, this is our true value. is close to 3. Let's use 3 to calculate. G prime of 3 is 9. You see, this number is greater than 1. So big. Okay, so if we want to converge, the error bound should be less than equals to the rate of constant should be less than 1. Then your error is smaller. If the factor is over 1, the error is not getting smaller, the error is getting bigger. So it won't converge, right? So that's why it diverges. Let's look at the second one. Second one was what's the g of x? 20 over x squared minus 3. 20 over x squared minus 3. So g prime of x, well here, this is like 20 times x squared minus 3 to the minus 1. We use chain rule. So minus 20 over x squared minus 3, square times u prime, which is 2x. Alright, so the answer is minus 40x over x squared minus 3 squared. When we plug in 3, let's see what happened. Minus 40 times 3, 120. 3 squared is 9. 9 minus 3 is 6. 6 squared. Wow. This, we can carry out this, and we can also get rid of 2. We get 3, and this is 10. Is that okay, everybody? Alright, and you can see this number is the magnitude. So the magnitude of it is 10 over 3. It's still greater than 1. Your error is not getting smaller, it's getting bigger. So this also diverges. Okay, so still big. Bigger than 1 is big. Okay, we want the error to be smaller. We want a factor that is less than 1. Okay, lastly, that is cube root of 3x plus 20. 3x plus 20 and cube root. Okay, chain rule 1 over 3, 3x plus 20 to the minus 2 over 3 times chain rule, which is 3, right? Oh, this is the same as 1 over 3x plus 20 to the 2 over 3. So when we plug in 3, we get 3 times 3, 9. So 29 to the 2/3. Good. This guy is less than 1. Okay? And so this is like the rate of convergence, right? And our order of convergence equals the p equals 1. So far, so good, everybody? And furthermore, if like our previous examples, if your first derivative is 0, your second derivative is not 0, then the order of convergence is 2, and the rate of convergence is the second derivative evaluated at the fixed points divided by 2 factorial. Okay, and I put approximately equal because our true value is not 3. The true value should be this guy, 3.0808594.6. Okay, then when we plug that into G prime, that is the rate of convergence. Okay, but here we just use 3 to calculate because it's easier. All right, so far so good. So we can see from the function g, the formula of it, to tell whether the iterative scheme will converge or not. Okay. So any function, any nonlinear functions, we can make up several iterative scheme, and then we can use this method to compute the list of the iterations, right? And then we can also tell whether the sequence is converging or not. Okay, so that's it for chapter 2. So please go ahead and complete your homework and the practice exam. If you have questions, feel free to ask me. So on our website, I also give you the chapter 2 practice problems. So you have our practice exam and the practice problems to practice. Okay, so please ask me questions. All right, have a nice day. Bye.